I'm Doug Hoffman. I've earned my gray hair by playing with programs since Dirt was young, back in the card punch days and 4-hour turnaround waiting for the printout. First computers that I programmed I never saw. In fact, I never saw a key punch. That just would hand off the coding sheets and got back printouts. So that was a long time ago, I tell people that I've been a sinner and now I preach. I've done programming, bachelor's in computer science, and early on got into quality in large part because I see that that's a field within software engineering that is neglected, underappreciated. I'm glad to see that in recruiting for the software engineers in testing, they have to pass muster both of development and for the testing. Very encouraging to me because it's a move up when you move into testing from development. It's a much more complex problem to be able to figure out whether or not a piece of software works. From an engineering standpoint, it's much more complex to design tests for what could go wrong than to simply create code that does something. And so our job in quality assurance, our job in testing is actually much tougher than the development engineers' jobs. Now, they don't know that, of course. Managers often don't know that, but we do what we can, right? So my background, as I said, spent 10 years at Hewlett-Packard as an engineer, moved into management, and have been doing consulting in the field after a bunch of startups back in the 80s. I've worked as a consultant now for about 16 years, working in the field, not just in testing, but in quality, not just in software, but hardware and computer systems. And so if you take a look on softwarequalitymethods.com, you'll find papers that I've written and presented and published. It's pretty wide-ranging. But one of the things I've really, really enjoyed in the last 8 years maybe, is the realization about test oracles and the role of oracles in test automation. And so that's what I'm going to be talking about today. Before I get going, how many of you are SETs? Okay. SQAEs? Okay. QA testers? Okay. Other? Okay. And for other managers or? Okay. Engineers? Engineers? Cool. Cool. I got into this in large part, I don't like to say it on film, but I'm lazy. I want the computer to do the work. And I want the computer to do the work if it's possible to get the computer to do it more easily than me doing it myself. If it's harder to get the computer to do it than to do it myself, then I'll manually test. There are exceptions here, but we'll get into that in a bit, I'm sure. So, active professionally, I've been working with some of the prime people in the software testing area for the last 10 years in particular. Have done consulting gigs with Kem Kaner and James Bach, if you're familiar with names I can drop. But have had the privilege of working with a lot of people who have challenged my ideas, have helped me grow the ideas. And the Los Altos Workshop Series has helped. And this topic, in fact, about 7 years ago, was a topic of discussion at several days workshop, like the Whopper that I was attending here last week. Questions about my background? Okay. Feel free, as I'm talking, to interrupt. If you don't understand something, it's probably me. And certainly, if you have a question, probably other people here have similar questions. So feel free to interrupt, because you're not really interrupting. I will tend to digress into areas as I feel the audience responds. So if you're going to sleep on something, I'll go to the next slide, and if you ask questions about it, I may stick around and elaborate. So if you'd like me to elaborate, ask questions. Anyway, I'm going to talk about models of software testing. Generally, 2 slides about automating software tests in general, and then oracles. How do you capture? What do you capture? How do you know pass, fail? So, you're all familiar with software testing, of course. Test setup, running a test exercise, and capturing it and comparing are generally what we do, right? In the execution of tests. When we can, before test setup, we have to design the test, we have to figure out what data, we have to work out what the environment needs to be and how to control it, all of that. And so I'm looking here at the execution of tests, and when we automate, how you run the software test. When we automate, we need to do these 3 things. And it becomes very interesting because we aren't using the human who tends to have 6 senses that we use. People will listen to the computers. We will notice flashes on the screen. And in some instances, I've actually discovered problems because set fire to something, it's burning up. So that buzzing sound. Printers, sometimes you'll do a reset and listen to the buzz. Hold that long enough. If you can figure out how to cause it to loop, it'll set fire to it.
I was just wondering if these slides are going to be available after the talk.
Yeah, I'll make them available after the talk. There's some stuff in the talk that is new, but nothing that I won't be happy to share. So when we test, we have a system under test. And typically we think about a test as having inputs and expected results, right? People generally agree that when we design our tests, we think about an exercise, stimulation of the software, and looking for results. There's a couple of other factors that we ought to be considering here. Preconditioned data. If what I'm trying to do is add a user to the data set, so have a new user, giving them an ID, it makes a difference. The behavior of the software under test is different if they are already there than if they aren't. And one of the things that we run into with automated tests, most of us learn very quickly, you can't just take a manual test and automate it, because you hard code the login name, and the second time you run the test, you get a different result, because First time, it's a new login you're adding. Second time, well, collision. Pick a different name because the name already exists. So the behavior of the software under test, definitely a function of data. I use that one example because it's pretty clear, but it depends on data almost every time. So anything we're testing, we need to be cognizant of the data. Likewise, the program state. You know, if we're not in the right screen, if there's an error dialog on the screen, you have to dismiss it before you can continue. When this is the computer being used to run the test, we know that. We see it. We respond to it. It's natural. When we automate our tests, not so natural. So the preconditioned program state makes a big difference in the behavior of the system under test. And the environment. What operating system are we running on? What's the traffic on the web? How big is the memory? Who's the current user? What permissions do they have? Make a difference in how the system that we're testing behaves. So factors from all four of these areas need to be considered. And when we automate our tests, we not only need to consider them, but realize that to the extent we aren't controlling, we aren't setting these, we may get very variable behavior from our system. And thus, with an automated test, we're going to flag it as an error because it's unexpected behavior. Need to be worried about that. Looking at the results, the outcomes from running a test, we have the test results, the thing that we expected to happen or looking to happen to tell whether it passed or failed. But there's also post-condition data sitting around that may or may not have been set properly. The post-condition data, for example, I'm adding the user to the list of approved users. There were 4,000 before, and there are 4,000 after. I can look at the results, and sure enough, the new one has been added. Somebody else got clobbered. But if I'm not checking all the data, I'm not going to know that. Right? So need to be aware. It's also the case when we are running our tests, we're making an assumption. What do we know about complex software? What do we know about whether or not it has bugs? It has bugs. It has defects. Okay? So the reason we're running our tests, in part, is to identify some of those, right? To try to figure out whether or not there are big ones. So when a defect is encountered, when it manifests, what is the result? What's the range of possible outcomes? Is it possible for some data other than that which you thought was being affected could get affected? Heck yes, happens all the time. Could even be the wrong data set that we write. We could clobber somebody else's files. Post-condition program state. Often this is very subtle. This is not necessarily just an error dialog on the screen, although that may be the program state we're talking about. But the internal state, many programs are state-based. And if you advance from state to state and you go into the wrong state, the result that we're looking at, if we're not checking the states, we may miss the fact that, yeah, It added the user, but now it's not going to allow any more users to be added because the program is now locked up. Can't get back there. And finally, when we run our tests, there are environmental results. The program could eat the bandwidth on the internet. Some programs leave files around. Been using Microsoft Word. Good example, right? For me, I keep finding these files on my system where I was editing something and I either renamed it and saved or Word crashed, and I have extra files. Here, there, everywhere, right? Temp files. But those are environmental results. Many of the attacks on computers are based on buffer overflows, buffer overruns. What are they trying to do? They're trying to get an environmental effect from under-designed programs. Poorly designed, doesn't do bounds checking, overrun the buffer, and suddenly you find you're in the operating system environment on somebody's computer. So when there are bugs in our software, anything can happen. Sometimes, as a human tester, we'll catch that because I had one tester I worked with working on printers, ran his standard tests and said, it's broken. And, you haven't even looked at the printout. How do you know it's broken? He says, because the pattern is normally click, click. And that was click, click. So it's broken. Just the timing. And you probably have experienced it as well. I've been sitting listening to the bang on the disk, right? And suddenly it stops. Things have gotten hung, right? And then it continues. Right? So there was an interrupt, possible problems. In our automation, we aren't going to catch that because we're not looking for it. We may not have means of detecting certain kinds of errors. So when we do our automated tests, we need to worry about factors in all these areas and realize that there's an infinite space of possible environmental inputs, probably a finite space, but huge for preconditioned program state, and it's infinite for the data, preconditioned data. It's a small infinity for preconditioned data, but it's still infinite. So we can't control it. We can't test for everything. All right? The game is always to pick the ones that are the highest likelihood, the highest impact for us, highest value. Okay, Hoffman's definition of fully automated: able to run 2 or more tests, a subset of all the automated tests. I don't consider it reasonable automation if you can only run every test you got, that it just walks through the directory and runs everything. Right? Yeah. It should operate lights off if it's automated. Now that lights off is on the assumption that everything goes as anticipated, as expected. If things don't go as expected, well, all bets are off. We've found something interesting. This is valuable. Right? We may stop testing and wait for a human. We may log a bunch of stuff and stop testing. We may log a bunch of stuff, skip some tests, and begin again. Lots of different things can happen if we run the tests and we find an error. Where most automation, I find, falls down is on either setting up or more easily recording the relevant test environment. What are the test parameters? What tests are we going to run? What system are we running on? What's its configuration? We all run automated tests. Okay. When you run an automated test, it logs the results someplace. Okay. Many of the commercial tools don't tell you what the environment is. And I can say from personal history, a week or 2 weeks after I've run the test, knowing the name of the system I ran on isn't really helpful because the configuration has been changed. Right? The mix of software on that system has been changed. So knowing the name isn't nearly enough. 6 months later, the name is meaningless in terms of, that system no longer exists. So I can't recreate the environment to reproduce the problem. Okay? And when we run automated tests, we're capable of running hundreds or thousands of tests a day. At the end of the week, you may have 50 log files you've created. And I know I can't keep straight 20 log files in a week, 50 a week for every week. Got to have that information in there or it's lost. And if it's lost, it isn't going to be recovered. Running the test cases is what most people think of as automation. And that turns out to be the trivial part. Capturing relevant results, keyword relevant. Keyword. What's relevant? Well, if there's an error and you need the information, it's relevant. If it's the information you need to detect an error, it's relevant. And if you didn't get it when the error occurred, then you may be up the creek, or the developer may be up the creek, because if it's not a reproducible problem, it's gone. After capturing relevant results, I asked the developers, by the way, for what they consider to be relevant. But comparing actual with expected results, this is done in a lot of different ways, and this is part of the Oracle issue. In fact, this is where the Oracle is. How do you get the actual, and how do you do the comparison? Oh, excuse me, the expected and comparison. And then reporting the analysis of pass-fail. So, hard parts of test automation, getting the stimulation, i.e. setting up the conditions, setting up the preconditions, identifying what is the data set, what is the program state, what about the environment, do we need in order to be able to run this test, and do we have so that when I run the test, if something goes wrong, I have relevant information. If I try to add the user, and it comes back and says, duplicate username, it's too late to go back to check to see, was it really a duplicate? Because I tried to add it. It may have added it. It may be a bug. Right? That won't allow me to add somebody because it puts them in there and then it checks to see whether or not they're in there. I don't know. So I need to have checked that before beginning the exercise. And then running the exercise, which is most often not a big deal. Capturing the results, identifying the information that we want to monitor. We're going to be looking at a subset of the information. The right-hand side of that diagram, some subset, not just what we call results, which are the obvious expected manifestations of the behavior of the software when we did this exercise. We want to check other things if we're going to have excellent tests. The reason I put this in blue is that this is a major prelude or precursor to the oracle. And when I'm doing automation, often I identify the information I have an oracle for in order to figure out what results I want to capture. So I back into it. And so differentiate the expected from unexpected behaviors. Knowing what the expected outcome is critical. Comparing actual with the predicted or expected, and then being able to know pass from fail, and I'll talk about this in a bit. Yeah.
And what if you test an application that is heavily used in what-if scenarios? Like, for example, ECO, engineering change orders, or supply chain management, where you just provide a certain set of, like parts and bill of materials.
Mm-hmm.
And then the application is supposed to calculate the optimal way of discontinuing the product and create a new one.
Okay.
Which is a simulation, and unless you have unless you know exactly what's going to be there, which is pretty much impossible because the data vary, you need to run the simulation, get the same simulation to get the expected result. So you wouldn't know what the expected result would actually be unless.
Yeah. So the question is, how would you figure out what data? And that's what the rest of the talk is about. So ask the same question again later if I haven't answered it in the talk. Because how do you know what to look for? How do you know what to put in? How do you know to set it up? Yeah, that is the Oracle problem. And this is a really hard question to answer in a lot of cases. In some cases, it's not that hard. But most of the time, we don't have a magic way of knowing what to expect. But I've got some clues here, some suggestions on where to go. And a hard part of test automation that I'm not going to be addressing, how do you recover when something does go wrong? When you find an error, how do you capture it? What do you capture? I talk about dumping the world. Any values, any environment information, everything that could possibly be relevant when we notice that there's a problem. And can you recover? Do you want to recover? Do you want to just stop and wait for a human to investigate this? So there's always the question in test automation of how do you deal with it when you have an error. Okay, so what is a test oracle? Mechanism by which we tell whether or not the software is behaving. Is it behaving or misbehaving? Is this what we expect to happen or not? Right? It's a combination of the information, being able to say, this is what we expect, and comparison, being able to say whether or not what we expect is what we're seeing. And for automation, the information and the comparison have got to be done by the machines, got to be handled by the machines. So I can't just bring up two screens side by side and look to see whether or not they're the same thing, because the computer can't do that. I have to figure out how to get the files in the same place. Okay, so the oracle is how you tell pass from fail. It's how you figure out the verdict from a test. Okay. So there's a couple of kinds of oracles. Most people think about deterministic oracles. It's the right answer, right? Binary. If it anything other than 4, wrong. 4 is the answer. Probabilistic oracles, and I'll talk about heuristic oracles in probabilistic, but it doesn't categorically mean a mismatch is an error. What it means is a mismatch needs to be investigated because it probably is an error, more likely than not if we've designed the oracle well. When we test with an oracle, one way to consider it is that the oracle may be generating the expected results. In this case, it appears that they would be running at the same time. Right? So whatever information environment is being fed to the software under test, we feed to the test oracle. And the oracle provides some subset. Actually, we feed a subset of the information into the oracle and get a subset out. So the oracle might be a description of the state, the menu tree, the displays and menus. And so we have program state. And that description is compared to the actual behavior as we walk through the system. Right? And so we have the actual state and the predicted state, and we compare them. For manual testing, often that model, the test oracle, is a model we build in our heads and is not explicit, is not written down, is not something that we are looking at and consciously comparing the behavior. In some cases, we are consciously comparing. We've got a flow chart, and we are mapping out where it goes. But the oracle itself is something that we always use, whether you're conscious of it or not. Every time we run a test, we're using a test oracle, because we are making a determination if it passed or failed. And we're comparing it against something, some expectation, and that expectation is the oracle. Okay? Now, I'll go into more detail on what I mean by that in just a little bit. We may have multiple oracles for the same test because, as I just said, we may be looking at the menu tree. But in that same exercise, we may be doing checks of arithmetic. We may be checking to see that data gets put into the data set, the database, correctly. So we may have multiple oracles that we're feeding at the same time, or we could have one oracle that gives us all the information or gives us multiple pieces of information. Right? So logically speaking, we can pull the oracles apart or push them together. But ultimately, we're going to feed some subset of the input world into the oracle to get some subset of the result world, the outcomes, in order to compare. So when we use the oracle, we may be comparing against stored values, and I'll talk about A/B compares. This is the most common way tests are automated. We have a golden master. We have the answer someplace, and it's stored. We compare against it. We may have computed values. We may have an algorithm that produces expected results based on the inputs. So we may have a routine that computes square root. And the software under test computes square root, and we feed the same input values to both and look at the answers and compare them.
Yeah, but here we have a paradox, because if you have two software programs that do the same, like for example, computing a square root, how do you decide which one is better? And if, for example, testing algorithm is better, then it should be actually transferred to the actual application because it is better, and then you have the paradox again.
Yeah. Let me get into that as we get to it. But the oracle has to be trusted. It has to be, quote, correct to some degree. And yes, sometimes that oracle may be as expensive or more expensive than the software that we've created. But it may be the GNU library, and we're not going to put our source in the open source world. So we've written a routine to do the same thing, and we can use that library for test purposes to compute the square root. So there are circumstances in which I may go out and buy somebody else's square root function for heaps of money just as an oracle. Okay?
Yeah, but it still doesn't answer the paradox question, because
Well,
when you compare it to, I mean, the best one should always.
but you may not have that alternative. That best one may not be available in the real application world. Okay, it may be available in my test world only.
And could it also be that there's something that's more reliable and more expensive, maybe a simpler brute force algorithm?
Maybe 1/10 the speed. So it runs 10 times slower. Doesn't meet our needs in terms of speed, but it's more accurate. Okay, so just trust that there might be circumstances in which it makes sense. You are correct that there are circumstances where it doesn't make sense. But trust me, computed values, I've done it lots of different ways, and often we've invested heavily in coming up with that. Usually not, but in extracted values, Noel Nyman has written some papers, and I've talked about embedded oracles, putting SVD is what he calls it, self-validating data. But you can put the answer or some key to generate the expected answer in the data itself. And based on that key, untangle and generate what the record's supposed to look like. So we can have the value built into the data that we are manipulating. It's a way of computing it, but it's funny. We have comparators where we have to worry about equality, right? Most of the time, we're comparing against the golden master. Is it the same or different? Right? If it's the same, great. If it's different, it's an error. Sometimes it works the other way around. If it's anything but this, it's okay. Right? So I may be looking for inequality. That I'm looking for a specific condition, which is an error. And so if that condition comes up, I found an error. But anything other than that, I haven't found an error, or at least I haven't found the error I'm looking for. We may have fuzzy comparisons. When I mentioned the two screens, well, those can be bitmapped. And given a bitmap in the computer, we can do comparisons. And if you've anybody done this? Yeah, you haven't. Trust me, it's possible for there to be a 1 pixel shift, and you don't want to have one dot out of place necessarily trigger an investigation that there's a bug in your program. So you may want to do fuzzy comparisons. Worked at Adobe with PostScript testing, and the really interesting investigation into fuzzy comparers and how do you compensate for certain kinds of conditions. And then there's heuristic rules I'll talk about, which rules of thumb. Rules that apply and will usually lead you in the right kind of direction, but will always catch the errors and may sometimes even tell you that there's an error when there isn't. Heuristics. So comparisons, and then we have the temporal relationships. Time, right? We may compare as we test, or we may compare after the test is finished. Right? We may generate the expected results, or read them from stored values, or untangle extracted values as the test executes for concurrent comparison. Or we may store the results and compare after that. And it makes a difference, but in different situations, we'll choose different ways. Subsequent verification doesn't make a lot of sense when you're dealing with terabytes of output. You probably want to do that concurrently if you can, so you don't have to have 2 copies of several terabytes laying around.
So regarding the comparators, when we talk about first to equality, inequality, it's very easy because you know exactly what you're going to expect.
Yep.
When it starts getting fuzzy, then you have to start putting some amount of logic into your test algorithm itself.
Yep.
And then I think this goes back to this question of, it's not really a paradox, but it's close to the fact that you're almost recoding the system again, because if you have to fuzzily know what's going to come out of the system, you almost have to recode the logic that you put in the first place.
Well, let me take the example of PDF. Okay, yes, the question is, when we have fuzzy comparisons, you almost have to recode the application in order to be able to figure out whether or not the result is correct or not, right? Not really the case with the PDF example, right? The fuzzy comparison is between 2 bitmaps of screens, 2 arbitrary bitmaps. Once I figure out how to do a comparison of 2 bitmaps to say, these are really, really, really close to one another, I'm going to ignore the differences, or these really aren't like each other, somebody better look, right? So the fuzzy comparison mechanism may be very complex. It may be as complex or less complex than the application I'm testing, because it's independent of the application I'm testing. It's dependent upon the nature of the problem I'm trying to solve, which is a result comparison problem. So it isn't direct. It makes a difference if I have one PDF that I generate and I'm going to compare, or if I have 50 million different PDFs I'm going to generate, and my choice is to have a person sit down with a light screen and look at pairs of printouts, or I get the machine to do it. Because the machine can do it and doesn't get tired, doesn't fuzz out, doesn't need coffee breaks. So when we start talking about the comparators, the equalities and inequalities, as you said, are really straightforward by comparison to the fuzzy comparisons. And the heuristic rules frequently are built into the test, not into the automation mechanisms. Okay. Again, I'll talk to that in just a minute.
Actually, you just mentioned that Oracle would be less or equally
complex
as application and test.
Mm-hmm.
But actually it should be equally or even more complex, because if Oracle is to be trusted. As a simple example here would be, let's say you're a university professor, I'm your student. So you gave the test, I failed a couple of the questions. I would never know what would be the right, if it's not a multiple choice, of course, what would be the right answer. So you would tell me what the right answers would be because you know more than I do in this particular case. So the same with Test Oracle and the actual development. Because Test Oracle has to know more about application and be more sufficient than the actual process.
However,
To point out the mistakes.
Yeah. So you're saying that the application has to be more complex because, as with a professor, grading exams has to know a superset, have more information, be bigger, better, faster, whatever, and therefore is always going to be more complex. And you're limiting your thinking, really limiting your thinking. I have an analog computer. It'll do integration inherent in just the electrics, the electronics. And so I can give it voltage levels and patterns of information that aren't in digital form, and it will return to me the integrated values immediately and very accurately. Extremely accurately because it's analog. It's the analog to digital conversion that has to be accurate. And that's a hardware conversion. Right? So I can derive the answers from some other thing than a program in some instances. I may be able to do my comparisons using other equipment, some other location on a mainframe where there are available resources that aren't available in my test environment or to my users. And so I may have a relatively cheap, well-established Oracle, one that we can really trust, right? Because it's been out in the world for 20 years and people have used it, depend on it, banks run on it. And so when it computes square root, we're pretty sure that this gives us a value that we can accept. So sometimes, yeah. And particularly when you're dealing with oracles for algorithms, code, new inventions, right? You don't have available oracles. But don't limit your thinking there, because there are many instances in which we can have oracles that are inexpensive and very powerful.
Yeah, it's true, but like you correctly mentioned, for something that's been there for like 20 or 30 years, but if you have a very complex algorithm, for example, Google search algorithm, let's put it this way, there is nothing like that in the world. At least I hope so. So you can't create something comparatively.
Okay, so we very quickly can rule out equality because we don't have a known mechanism for generating expected results that we would trust more than the Google engine, right? But fuzzy comparisons or heuristic rules, we may be able to apply, and we can come up with oracles for fuzzy comparison, for heuristics, and I'll show you in just a few minutes what I mean, and we may be able to do some very powerful testing, although we aren't getting the equality or inequality level responses. When we talk about the oracle, we can talk about the completeness of information. How much of the stuff on the right does it cover? How much of the stuff on the left does it take as input? Does it consider? Accuracy, talking about the number of digits of accuracy. Whether or not it's generating parallel information or generating the actual expected results. So we may be looking at a system that does the same thing in a different way, and therefore it may have a different menu tree. We're looking for the functionality to compare, not the mechanisms, not the tracing through the programs. The usability of the oracle. 2 screens. It's not in machine form, not in the same system. In many instances, we may have analog inputs, as I mentioned, versus digital. We may be testing radar systems And if we're testing something that is unpredictable to begin with, the inputs are unpredictable, then it may not be usable, even though we have an oracle that just isn't going to work for us because we can't get there. Maintainability. When something changes in the software we're testing, what happens to our oracle? And how much work does it take to make that oracle usable again? This is the big problem with most GUI-based automation using the capture tools. That as soon as the GUI changes, the tests all break. Right? Their oracle is hard-coded. It's expecting to see this screen, and we're doing a comparison. And if that screen changes, the comparison fails, we have to rebuild the automation. Complexity. Exactly what you're saying. You know, the oracle can be complex, and if it's more complex than the thing we're testing, we may begin to question whether discrepancies mean the oracle's broken or the software we're testing is broken. To the degree the oracle broken problems come up, we're wasting time because we are finding out nothing new about our application under test. The software under test may work, we don't know, but we're spending time troubleshooting something else if it gets too complex. And cost, direct and indirect cost. Okay, so for example, we might use, for testing of spreadsheets, the last version. This can be used for a lot of different kinds of applications. Version n-1, and compare it to version n. This, you're basically saying, is it consistent? Is it the same as before? And using that oracle, we can feed arbitrary inputs into either or both and get back responses. What about revised functions? Okay, if that function was revised from n-1 to n, we expect miscompares. How do we exclude that, or how do we test the ones that have been revised? And there's a problem when we do this of the legacy errors. There are errors in version n-1, and when we check version n, it has the same error, and therefore gets the same wrong answer. And therefore, we pass it. Okay, and in some instances, that after so many generations, when they figure out that there's the error, they can't fix it, because the square root of 5 is always 2. Right? Database management. For example, we might use the same data set, use 2 different SQL query engines using the same SQL queries to make sure we come back with the same data, the same rows. So we might use one database management system as an oracle for another. And bit comparisons of screenshots I've mentioned. Expected variability. In many instances today, printers, displays are told this is a 10% gradient, and given the corner coordinates, and the hardware at that end generates the 10% random dots. It's not predictable. And the next time you tell it to display the same thing, it's a different random set of dots. So we have expected variability that is extremely difficult to extract out. Fuzzy compares are required. And then we have the legacy errors and the golden masters. the screenshot may be wrong, may have an error in it. Or it may be just a little bit different this time, and when the developer looks at it, they say, oh, close enough. Just use the new version as your golden master. And after 50 times doing that, your golden master looks nothing like what it's supposed to be, because it slowly over time has morphed into something else. Okay? I hear somebody giggling. Never happened on your watch, huh? So deterministic reference functions, these are the ones that we're going to use equals or not equals. The saved result from a previous test run. Probably the most common way we compare. Parallel functions. We've talked a lot about that. Previous versions, a competitor's product, a reference standard that may be on the mainframe, alternate platforms of the same application. We compare running on Unix with running on Windows. Or we may create a custom model that runs in parallel. Sometimes we can use inverse functions. We can merge a table that we split and see that the merged table is the same as the original table. Right? Split, merge, compare the after. So we may be able to look at the output, the results, and answer the question, is this plausible? Is this the likely output? If I am looking for whether n squared works, right? 2 squared, well, let's take 3 squared, because 2 is funny, because 2 plus 2 versus, but 3 squared is 9, right? May not have an easy way of knowing whether 9 is correct, but if I trust the square root, I can take the square root of 9 and come back with 3 and compare, 3. It's plausible. If I took the square root of the answer of 3 squared and I come back and the answer is 4, something's wrong. Right? The square root of 3 squared ought not be anything other than 3 or negative 3. So mathematical inverse. And sometimes we may use as a reference function useful invariant rules like sine squared plus cosine squared equals 1. So if we're testing the sine function and we have a cosine function available that isn't based on this code, doesn't share code with the sine, then we can square the sine, compute and square the cosine, and it better equal 1. Okay? Because that's a mathematical invariance. So for deterministic functions, also, we can encode what we expect to be the answer right into the data. We do this when we print. This line should be 48 characters long, or whatever the number of characters is. Right? So the answer is right there in the information. Probabilistic reference functions, we may want to look at the statistical parameters. I was looking at the 20% project out in the lobby with the world showing the current activities. If we did a statistical analysis of where those activities were coming from, correlated with the time of day, if that significantly changes right now, right? In Silicon Valley, it went from 5% of activities to 35%. And it stayed steady state at 35%. you might draw a conclusion that there's a problem someplace. Because the mean is significantly different. It's way outside the parameters. We may be looking at a predicted distribution that says that Silicon Valley is between 4 and 6%, or 3 and 8%. These numbers are coming off the top of my head. I have absolutely no idea what they actually are. But we have a predicted distribution, and when it goes outside that, we have something to investigate. And if I sort them in sales order number order, I should get the same sort order as if I look at the time in which the order was posted, which is the time that the number was allocated to it. And if I do a sort on the time, I should get the same sort order. Okay? Yeah, there may be nanoseconds off, and I may get things out of order, but that's why I'm talking about probabilistic comparators. Okay? It's possible that we come up with an error, but normally that would be a good double check. We may be looking at apparently incomplete attributes. And here we're dealing definitely with a heuristic. In the US, zip codes are 5 digits or 9 digits. So if I do a load of a database that includes names and addresses, I can very quickly scan all of the US addresses for zip codes that are other than 5 or 9 digits. And if I find any, there's a bug. There's a problem. And the kinds of problems that we're catching here, if there's a bit shift or a byte shift on the load, if we get the wrong column, those problems will show up very, very quickly. There's no guarantee that the zip code, which is 5 digits, is the right zip code. But we can catch some errors this way, probabilistically. Parent is usually older than the child, right? I'm older than my kids, but is that always true? Adopted kids? Second marriages? Yeah, it's possible. You could scan through a set of data, employee information, and find that some employee has a child older than them. But if we're looking for likely data errors, it's much more likely if a child's older than the parent that there's a problem in the data. Much more likely. Right? And it's not hard to very quickly scan huge amounts of data for this kind of inconsistency. And then, two parallel math functions. So we may be looking at the arithmetic value without taking into effect what effect running that routine has on the Ethernet, on other programs, on the operating system. The state of the program itself may be wrong after it does the computation. We're not checking for that. So even when we think we are checking complete attributes and checking the results, there's a whole lot out on the right-hand side of that diagram that could be going on, that could go wrong, and we aren't going to see it. So, 5 strategies. No oracle. I'll talk about very briefly. True oracle, which is what most people think of, and that's having an independent generation of the expected results. It's having some other mechanism that is generating the answers. Consistency oracle is the n-1 versus n run. We're asking the question, is it the same or different not the question right or wrong. Self-referential, or buried in the data itself, is the answer to what the answer should be. And then heuristic oracles, which is where we are looking at some characteristics, often incomplete. Okay. Yeah.
Just to clarify, so basically your test oracle is pretty much the expert system for a given application.
Well, for a given test.
For a given test,
Yeah. Okay. Yeah, the oracle is the expert system that's providing the answer for a given test. And pretty much. And it ranges from no oracle at all to what I call a true oracle, that you really trust it, it's completely independent, and it gives us all the expected values that we're looking for.
And I'm sorry, I mean, maybe if you cover that later, I mean, we can get back to it later, but you have a whole bunch of experience in, creating oracles and as a consultant for consultancy for companies in that field. But, I can imagine a company like Google or Microsoft, for that matter, or Adobe, doing something like that. But, for example, for a startup, the investment in creating Oracle would be sometimes more than they, decide they can afford. I mean, there is also that factor that we have to consider. I mean, how willing the company is to spend money on developing oracles, especially the good ones.
When you are running a test, you have an oracle, or you're using a no oracle strategy. The oracle may be built into your test and may be hard-coded that 4 is the answer. But there's an oracle. If you're checking to see the result, what you're checking is what you're applying an oracle against. So every test uses either no oracle strategy, and I'll describe that in more detail in a sec, or you have an oracle. We can't avoid that. When we have automated tests, we have oracles. It doesn't have to be a program that we implement. It's how do you know the right answer? How can you tell whether the test passed or failed? When I automate, I look for oracles that allow me the flexibility to be able to do massive feeds into my software under test, to do random checks of my software under test. But that's not the only reason. And if you can't do that level of oracle, there may be other ways to get valuable information about whether the software is working using heuristic oracles, consistency oracles, that are very powerful. A consistency oracle doesn't tell us pass from fail, but the information about whether this run gives us the same results as the last one is extremely powerful. If it's different, we have to investigate. Either they fixed something, or they broke something, or in a rare instance, they changed something that really doesn't matter and we checked it anyway. But usually we're looking at either they know they fixed it or it's broken. Right? And so it doesn't matter so much how you got the data from the first time if all you're really trying to do is tell, did it change? And you can generate massive amounts of data, and you can compare on many different levels. You can grab the whole database, right? Compare the end result data sets. And we're not going through and making sure every byte is correct. And if we're not, what we're telling is every byte the same as last time? Right? That's something computers are really good at. Okay? So consistency oracles, very, very often used, and very often mistaken for real oracles with validated data. No oracle, trivial, right? Runs fast. There's no overhead involved at all. You only notice spectacular errors, right? If the system catches fire, you might notice. You did an over the weekend run, and you come in on Monday morning and take a look. If you had no oracle, what does that mean? It means that your program ran and finished. And if your program ran and finished, obviously you passed. How long did it run? Well, no, we're not checking. We're not using any oracles. Did the program terminate abnormally? Don't know. Only a spectacular error is going to come up. One team I worked with spent 2 people years developing an application that used the program API, and they generated every function call that the application could use, and used random variables to generate all kinds of combinations and statistical distribution of inputs, and they could bias it this way and that way. 2 people years of development. My first question to them was, how do you know if it did the right thing? And I got two deer-in-the-headlight responses. Huh? How do you know if it passed or failed? Well, it terminated. This is a Unix system. Abnormal termination, the program not being there, and normal termination look the same, right? I got a carrot. How do I know? Oh, well, we hadn't gotten that far. Aha. Yeah. It's silly, right? 2 people years invested to find out if we can set fire to something. If somebody's sitting there watching and it only takes 4 seconds, then maybe you'd notice. But yeah, the oracle strategy can be very cheap for no oracle. False sense of accomplishment. Was talking with Harry Robinson, who's now at Google, some years back about the spectacular errors. And Noel Nyman, actually, at Microsoft, was the father of the dumb monkeys. Dumb monkeys are just key punchers, key pushers. And early in the life of products, they use dumb monkeys to test. It just feeds a series of random characters into the application to see what happens. If it crashes, a spectacular error occurs, it's interesting and valuable. The oracle is, does it crash? The reason this is useful is that at some point, it's cheap. It doesn't take much at all to write a stupid monkey, an executive monkey in particular, one that just pounds on keys randomly. Generate a character code. 0 to 255. And just do it again, and do it again. So it's very inexpensive to create that, and the oracle is no cost. And if it crashes, there may be some really valuable information to be derived, particularly if you've captured the last 50,000 keystrokes, so that the development team can investigate and figure out what was going on. So sometimes the oracle strategy is a valuable strategy, but you've got to be really careful, because a false sense of accomplishment, the fact that it passed the executive monkey test, random characters shouldn't crash an application. So the fact that it passes doesn't mean, not crash doesn't mean not fail. Not crash means not crash. You're only going to catch spectacular errors. the other end of the spectrum, the true oracle. Here we have an independent implementation. So we have as little in common as we can get away with between our oracle and the software that we're testing. If there are common subroutines, we have the possibility of common mode error, the same error occurring in both applications because of some library routine giving us the wrong result. So to the degree we can make it independent, it becomes a better true oracle. We can identify the input ranges where this will be generating the right answer. It may be limited ranges, maybe limited values within the ranges. So it may only work on positive numbers, although negative numbers can be input, but it isn't going to tell us for negative numbers because it's not covering all the input space. Likewise, the result range may be limited. It may only have certain kinds of results it can generate. But for the input range and the result range that we've identified, we have a true oracle. Correct, trusted results. Usually expensive, and it's never complete. Even though we may think it's complete, it can be complete over some input range, some result range, but think of the diagram again. It's never complete over all possible inputs or all possible outcomes, and therefore not a true oracle or not a complete oracle ever. The consistency strategy, I call it A-B compare. You have some golden master, some stored result, and you check for changes. The regression checks, we're checking for changes. Frequently, we have unvalidated data. People may think that golden master is correct, but nobody ever went through that 0.5 megabyte file and checked every bit in every byte to make sure it was correct. What most often happens is somebody scans through, and even then kind of flips through the pages and doesn't see anything obvious, and therefore it's the golden master. That's okay. In fact, the consistency strategy is extremely powerful. Just be careful, because we delude ourselves into believing that this tells us it works. No, it tells us it works the same way it did last time. It may not have worked last time, maybe errors in it. We don't know. But we don't have new errors being turned up by this test, and that's a powerful piece of information. It's also inexpensive to find out in a lot of cases. We may be able to use alternate versions or alternate platforms, or a foreign implementation. We may be able to use someone else's spreadsheet to test our spreadsheet, someone else's search engine to compare to ours. Are we consistent is the question that's being asked or answered. Okay? So the consistency strategy for automation, for oracles. The self-referential is a strategy that I've explained in my papers on oracles, and Noel Nyman, N-Y-M-A-N, Nyman, yeah, Microsoft has written several papers on SVD, self-validating data. And so basically, we're going to embed the answer in the data itself. So the message that we've embedded, written as a record to the disk, says, I'm the first record of the file. I'm this size. Right? So many fields. So the expected results are right there. And when you look at the file independently, you can tell whether or not that record is the first record of the file and whether it has the characteristics that are described there. Identifying a cyclic algorithm and a seed. In my papers, I describe a data communication test in which I generate a message with an initial value and a cycle, repeating cycle. Transmit the record. At the far end, I grab the record and reverse engineer it. Figure out what the seed was, figure out what the increment was, and how many values I got, and send back that tuple. I don't have to send the whole message back, and so we can verify based on the algorithm, knowing the cyclic algorithm. And another is embedded seed value. If you've ever used a random number generator on computers, they are pseudo-random number generators. And by pseudo-random number, it means if you start with the same seed value, if you give the random number generator the number 1 as its starting value, it will generate the same random sequence. Statistically, it's random, but it's a sequence that's repeatable. So given the seed, we can recreate the random sequence. If my data includes the seed, then I use that seed to generate n characters, right? I generate a value, random value that is the length of the string, and then use random values to generate the characters in the string. Given the seed value and using the same random number generator, I can recreate that same string. So self-referential data, I can write those records out to the disk, and then I can look at the records, and each one will tell me whether or not it's been clobbered. Is it still intact? And what's the integrity of this information? It's pretty good. Right? And so you could use that as one field that you check in a set of data to see whether or not you have general corruption problems. Doesn't tell you that the other fields are correct or not correct, but if you catch an incorrect value in this particular field, then something's wrong. And then the heuristic strategy, applying a rule of thumb. Right? It isn't guaranteed to give you the right answer, to tell you pass, fail. It may miss some errors, and it may generate false alarms. It may give you an error indication when it's not an error. I qualify the zip code with US zip codes. If you look at zip codes and don't qualify with US, the 7-digit, 9-digit rule doesn't apply. If nearly all of your addresses are US addresses, then you might go through and check the exceptions, because you would get false alarms on anything international, or you could for an international zip code. But the fact that it has 5 digits, or excuse me, 7 digits or 9 digits, no, 5 digits, 9 digits, that's right, doesn't mean it's right. It may not be my address here in Silicon Valley. Yeah. It may be a New York zip code for California address. Don't know, because we're using a heuristic. We're looking for particular kinds of possible errors. Okay, and we're looking for some way to do that cheaply. That if we find a miscompare, it may be significant, but it doesn't cost much to check. and it can find certain kinds of possible errors. The bit shift, the byte shift, data being clobbered. So Oracle's critical for automated tests. Critical that we be aware of the fact that we're using oracles and what oracles might be available, because there's lots of different ways to approach this and lots of different ways to evaluate the results, to do the comparisons. And by mixing it up, we can find some really powerful, inexpensive tests, automated tests, and get at more errors than just those that a human might find, or certainly more than the conventional take a manual test and automate it, and that's your automated test set. So some references. And further questions?
Do you have any suggestions on how to test systems that are going to be changing, like, or say how to, like, well, let's say you have a system and if you update it in one place, you also need to update it in another place. And how to design, say a unit test or some kind of test that runs automatically that'll detect something like that.
Okay, so the question is, are there ways of automating the testing for systems that are changing?
Yeah, for systems, right. Yeah, for systems that are changing, and particularly where you have some data structure that needs to be in two different places.
And the data structure may be changing?
Yeah.
Yeah. I mean, if you separate the test exercise from the oracle, and you may want to separate the oracle comparator from the information content. If you make the separations, you may find that the comparator will always work. You may find that you have some oracles, some information sets that are always going to work, or not. But if you can find where there's stability, you can apply some of these techniques. I've also successfully worked with a team who looked at upcoming structural changes in the data sets and were proactively updating their Oracle data sets to reflect the changes that were coming down the road, so that when they got the updated software, we already had preconditioned data that was ready, and indeed we're able to point out errors to the developers the first time where they had not correctly used the constructs that they had documented they were going to use, and they were actual bugs. But that's a matter of really understanding what your data is and how it's constructed, and managing that information. Other questions? Okay. Whew. Terrific.